Hi guys, sorry I forgot my microphone. Bear with me. Okay, so welcome to part 3 of this lecture about the assumptions of parametric statistical tests. And for the first time we're going to come to deal with the idea that there are some tests, statistical tests, which don't make all of those assumptions that parametric tests do, and they can be really useful in situations where we can't meet the assumptions in other ways. So let's have a look. This is kind of option 2 if your data are not normal. Option 1 was to try to transform them so that they are normal. Option 2 is to use a non-parametric test. In the case of the t-test, this is really the main situation in which we would need a non-parametric test, since there is an alternative test available if homogeneity of variance can't be assumed. And really the issue with independence is one of experimental design, that you either have designed your experiment correctly or not, but of course there is the special case of the paired t-test, which can help you analyse data which are in that paired form with that special kind of non-independence. Anyway, coming back to the here and now, we're talking about a non-parametric test as a solution to the problem of normality not being, or us not being able to assume a normal distribution. So the test we're going to look at has got another annoying name. It's called the Wilcoxon test. It's amazingly also got another name. It's sometimes called the Mann-Whitney test. And we're looking at the two sample or independent samples version of this test, which is the equivalent of the independent samples t-test. There are other versions of this test that are suitable, for example, for paired design. So life gets a little bit complicated here. What you'll find in the module handbook is a kind of test selector flowchart, which helps you, if you're sort of better at understanding these things visually, see a sort of map of the circumstances in which you need different types of tests, and you might find it helpful to refer to that when trying to remember how these things work. But let me just try and recap. For a bog standard vanilla t-test where you're comparing two samples of independent data, then if you can't meet the assumptions of parametric tests, you can use a non-parametric test, and it's called the two sample or independent sample Wilcoxon test, sometimes known as a Mann-Whitney test. Right, okay, so it's a test. It uses ranked data rather than the raw data, and this is the key difference really between parametric tests and non-parametric tests. They get rid of any information about the distribution of the data by ranking the data and turning them into ranks. So what we're going to look at is the difference in two groups of ranks rather than the difference in two groups of raw data. So by ranks, what I mean is we get the data, we put them in size order from the biggest number to the smallest number, and then we turn those into ranks. So the biggest number is number 1, the next biggest number is number 2, etc. And just like all stats tests, it's going to produce a test statistic, this time called W, and that is going to allow us to calculate, or allow the computer to calculate, a p-value. There is one peculiarity of the Wilcoxon test which it's worth noting, and that is, unlike every other test I'm going to tell you about, the test statistic goes the wrong way. The bigger the test statistic, the smaller the difference in the mean ranks. Don't ask me why. Whoever designed it was clearly not thinking straight. But it does mean that we're looking for small values of W to indicate big differences in the ranks between two groups. But the computer does the hard work for you because it will calculate the p-value for you. So really what you need to focus on in terms of significance is whether the p-value is less than your critical threshold, which is normally 0.05. So the two-sample Wilcoxon test, it's hard to say, like every other stats test, is a bit easier to understand with a real-life example. So I'm going to look at something that may be close to your heart, which is the subject of binge drinking. And we're specifically going to look at binge drinking in students, and a study I found in the journal Addiction, which was looking at the impact of heavy drinking, sessions of heavy drinking, on the performance of US college students in academic tests. And so what they did was they actually looked at students who'd been out on the razzle and got very drunk. The following day, did they perform worse in exams? And obviously this is a kind of, again, one of these popular hypotheses that people assume that if you've got a hangover, you're going to perform badly. But do we really know that? Well, let's test it. I can't remember in this study whether they actually gave the students, randomly selected students and gave them booze. that would be ethically quite problematic, but maybe they did, or maybe it's an observational study where they surveyed students who'd been on the booze and those that hadn't. Anyway, I think it was experimental, if I remember rightly. Otherwise, the confounding effects would be horrendous. The null hypothesis in this study was that the academic test performance would not be affected by heavy drinking the night before. And here are the results. We've got 2 frequency histograms showing the distribution of test scores in the exam for the control group who didn't drink anything the night before and the group who drank heavily. And it's difficult to see much about these distributions. They're kind of pretty messy. And I can tell you that when we analyse the distribution with the Shapiro-Wilk test, what we find is that they are not normally distributed. And we can't find a mathematical transformation which solves that problem. So we've got a fundamental problem. We can't run a t-test because the data are not normally distributed. So what do we do? Well, first of all, I just want to show the data in another form. Very commonly for data like this which don't follow a normal distribution, we might want to plot what's called a box plot. The box plot shows slightly different information from a kind of standard error plot that I've been showing you so far, which is typically showing the mean and the standard error. The problem with the mean and the standard error is that they are typically kind of associated with normal distributions. If the distribution is very wonky, very messy, then interpreting particularly the standard deviation actually, and the mean can get a little bit tricksy, and it's in those situations that people often resort to plotting the median, which, if you remember, is the middle value of a data set when they're ranked, and something called the quartiles, which basically are the different the points which divide the data set up into 4 quarters. So the median is effectively a quartile. It divides the data into 2, and then each of the 2 halves is divided again by another quartile. So the box here represents the upper and lower quartiles, and then we have the median in the middle, and then together with these whiskers, which represent the extreme values in the data set, the highest value and the lowest value, we end up seeing the 4 quarters of the data in total. So between the whisker and the upper quartile, that's the first quarter of the data. Then we've got the next quarter down to the median, then the next quarter, and then the next quarter. So a box plot shows you the distribution of the data divided into 4 chunks using these whiskers and quartiles. And it's a standard way of presenting data, especially where their distribution is not very symmetrical, not very normal. Anyway, the reason I've plotted it here is so that you can see, perhaps more easily than on this rather messy set of frequency histograms, you can see that the 2 groups of students, their test scores are fairly similar. The best performing student of all was one who was on the drink the night before, but the median performance for the control group is a bit higher than it is in the heavy drinking group. So that suggests that maybe there is an effect. Maybe the sober students are performing better, but we don't know until we've run an appropriate stats test. And there's a lot of overlap here, so maybe there isn't a difference. Well, I've run the appropriate test, which is the 2-sample Wilcoxon test, and I found a test statistic of 665 and a p-value of 0.2. And that means that there is no significant difference between these 2 groups. And this is actually what this study in the journal Addiction found, that heavy drinking the night before did not impair people's academic performance the day before. But before you all rush out there and think, right, the solution to happiness is to get drunk on the evening before an exam, the same study did find negative effects of this heavy drinking on people's mental health, essentially. So I would not advise getting heavily drunk the night before an exam, really. And of course, this is a relatively small study. It could easily be that the difference that we can see here is a real difference, but we haven't got the power to detect it. In other words, we've committed a type 1 error. Okay, so that's the Wilcoxon test, and it crucially relies on ranking the data. So just to kind of show you what that looks like, here is the raw data. We turn the raw data into ranks by putting them in size order. If we have 2 values which are the same, then we use what are called tied ranks. So here, instead of going 1, 2, 3, 4, because these 2 data points are equal, we give them the average rank that they would have had otherwise. So the average of 3 and 4 is 3.5. So once you've done that, then the analysis continues and compares the distributions of, or compares the mean ranks of the two groups. But the point really I'm trying to make here by showing you this process is that you lose information by doing this. By ranking the data, you lose information. The fact that this first data point is a long way above the second data point, and yet say these two data points down here are very close together, is hidden when you convert into ranks like this. And that means that the Wilcoxon test, like other non-parametric tests in general, is less powerful, less able to detect interesting effects than the equivalent parametric tests. And so this is one reason why we wouldn't just immediately default to using non-parametric tests without bothering to check whether the data are normal, because all things being equal, we would prefer to use a parametric test because it's more powerful. So Wilcoxon tests are obviously suitable when you can't transform the data away from a distribution that doesn't look normal, but they're also useful for data sets which are unlikely to be normally distributed in the first place. So they're quite commonly, they might be used for ordinal data which actually come in the form of ranks already. And as I said, I think earlier on, there is an equivalent of the two-sample Wilcoxon test for paired experimental designs, and it's called the paired samples Wilcoxon test. So if you've got paired data which don't follow a normal distribution, then you've immediately got a non-parametric alternative. So for the biology students at least, you're going to be navigating your way through the decision-making process here, looking at, say, a t-test. Is it suitable to do? Are your data suitable for a t-test? If not, do I need to use a paired samples Wilcoxon or a two-sample Wilcoxon, etc., etc.? And that's unfortunately the kind of convoluted decision-making process you have to go through as a scientist when you're looking at a data set. And the sort of principal purpose of this course is not so much that you memorize every single name of every test, although I will give you credit for that. More important, much more important in the assessment and for your scientific lives, is that you understand the underlying concept here, which is A, that we use tests in the first place to provide an objective assessment of a data set, and B, that we choose the test which makes appropriate assumptions about the data that we have. Because if we don't, if we use the wrong test, if we make unfair or illegitimate assumptions, then we end up with conclusions that aren't worth the paper they're written on. Okay, so that's the end of this lecture. The next lecture, which will be after Christmas, is going to be about how we deal with counts and frequencies, which is an issue I haven't really touched on so far. And then we're going to move from having looked extensively at differences in biological situations, we're going to look at trends, and in particular at the idea of running correlation tests, which you may have encountered before. Okay,